Thank you for the introduction. Hi, everyone. So this is a joint work with Mohamed Mansouri, who in fact very recently defended his thesis on this topic. So this was one of the first chapters of his thesis. Wafa Ben Jabara, he was at Thales at that time, now working at NXP. Wafa Ben Jabara from Thales and Mauro Conti from University of Padova. And this is a systematization of knowledge paper about secure aggregation based on crypto schemes. And we mainly investigated their suitability for federated learning, what we tried to find out, to identify what were or what are the challenges when trying to integrate, use secure aggregation, which was already existing before federated learning, into federated learning. So let me remind you what federated learning is. So we have a bunch of users who would like to collaborate, everybody knows it, who would like to collaboratively learn a model. And the main goal was not to be disclosing their local data set, so everything remains in-premise. And there's this server who initiates this training by sending some initial parameters, and then users locally train the model based on those parameters, update the parameters, sends those parameters to the server, who then aggregates those parameters, usually with the federated averaging approach, so computing the average of those parameters, send back the results until we just continue this periodically until we reach a good level of accuracy. And federated learning, as I said, the first goal was privacy protection, but then we witnessed, and thanks to the previous speaker, many privacy attacks against such a naive implementation. So from the parameters, we were able to learn through membership inference attacks or attribute inference attacks, reconstruction attacks. From the parameters, we were able to guess whether some sample was existing in the local data sets or not. And one way to cope with that problem was proposed towards 2017 was to use secure aggregation. What's secure aggregation? Well, secure aggregation was proposed for many applications, ranging from voting systems to smart meters, wireless sensor networks, until now federated learning since 2017, I think. So the idea is that we have a bunch of users who send some regularly, so periodically they send some inputs to an aggregator, and the aggregator mainly computes the sum of those inputs. And the main things that changed with time is that first we were talking about binary values. Now we're talking about a bunch of values, usually floating point inputs in the context of federated learning or smart meters. What are the security requirements? There was a very good paper in the previous session in the green room. The problem, the first and foremost problem is aggregator obliviousness, so data privacy. So the adversary should not learn anything more than the aggregate. That's the first, you have to ensure this property. And if we're talking about the malicious model, where either the user or the aggregator can be malicious, or both, in that case where we also need to ensure aggregate unforgeability, which means that the adversary should not be able to output an incorrect sum, an incorrect aggregator. How does secure aggregation works? We have three phases. First phase, set up online or offline, depending on the scheme, where in fact all the parties receive their keying material. So individual, like users, will receive their individual keys, and the aggregator will receive an aggregate key that will help it obtain the actual aggregate. Then during the protect phase, we use, each user uses its individual key together with the timestamp, because this is periodical, if you remember, to protect his input and sends this protected value to the server, the aggregator. And finally, during the aggregation phase, the aggregator uses its aggregate key together with the timestamp and all the protected values received from the users in order to finally obtain the sum in clear text. So as I said, we have investigated secure aggregation solutions based on crypto schemes. There are some other secure aggregation solutions based on shuffling, based on differential privacy mechanisms, based on TEE, trusted execution environments. Here we focused on crypto schemes mainly. Two groups, encryption-based, MPC-based. Under encryption-based, we have identified three main groups by analyzing the state of the art. Masking-based, additively homomorphic encryption-based, functional encryption-based, and secret sharing-based in the context of MPC. So we have studied, I have to look at the watch. So we have studied all these schemes. I had very nice slides for each of them, but for the lack of time, if you want, I can send you the slides, the backup slides for that. So we have studied those, and we have somehow evaluated the pros and cons of these schemes in terms of performance, in terms of infrastructure. So in the context of masking, the operation is very simple, very efficient. You just do a plus modulo P. But the main problem is that we're talking about masking, so those are used only once. So we have to generate masks each time, at each interval, at each round, if you want, in the federated learning case. And we need an online setup, so this has to be done in real time. On the other hand, additively homomorphic encryption schemes, well, it's not just a paillet, it's a multi-key, multi-party homomorphic encryption scheme, if you want. Every party has an individual key, and then there's an aggregation key that, in fact, aggregates all the keys as well. But we're talking about long-term keys, so we don't need any online phase anymore. And the main problem with those schemes is that, unfortunately, both masking-based and AHE-based schemes cannot cope with user dynamics. If a user drops or if a user just leaves the group, the aggregation set, let's say, then the aggregation that cannot happen. It's not, the result is not, it's bogus. I mean, it's not correct and it's bogus. We cannot retrieve it. There's the functional encryption-based solutions. Mainly, the idea is to get the key corresponding to the actual function, to be able to decrypt just the output of that function. And the function that is considered here is the inner product. One of the vectors is, in fact, a binary vector, 1, 0, 1, 0, and I put 0 when the user is offline. And I just do an inner product with the inputs of the protected inputs of the users. So user dynamics done. But online setup, because you have to receive the decryption key whenever, so the aggregator has to receive the decryption key whenever aggregation happens. And finally, MPC-based, well, I mean, when you just listen to the definition of privacy, this is the definition of MPC, right? So the idea is that we have several aggregators. Each user secret share its input, sends each share to one of the aggregators, and the aggregators collaboratively get the sum of get the aggregate, mainly. No key setup, but high communication overhead, my goodness. Okay, so there have been many solutions for secure aggregation, and very recently, since 2017, on federated learning. And what we have done is that we have tried first to evaluate, we have identified 7 challenges grouped with respect to fault tolerance, scalability. The purple one, I would call it accuracy, privacy, and verifiability. And we tried to identify some open research problems in order to publish other papers. Firstly, we have tried to see whether existing secure aggregation papers, solutions, not those who were already tackling federated learning, were addressing those challenges. And we see that privacy, maliciousness was not there yet, because it was not a problem for wire sensor networks. We were trusting the aggregator and the users. Then we have studied all the challenges, all the 7 challenges, and the solutions that were coping those challenges. So user dropouts I already mentioned, and the main solution to tackle these user dropouts is either not to use AHE-based or masking-based solutions, or use some secret sharing schemes to secret share the actual individual key to the users. And whenever someone is offline, the online users will be collaboratively recompute the actual key and compute the aggregation. In terms of scalability, we're talking about large data, so large vectors, large number of users, and floating point inputs, so scalability and accuracy. And to cope with those problems, we try to, some solutions try to regroup some of the users and deal with hierarchical federated learning. Some others, with respect to high dimension, there was the first talk as well, some to use some packing, some dedicated batch encryption solutions. In terms of privacy leakage, well, secure aggregation, I mean, the aggregate itself was a public information. It was not supposed to be protected. But unfortunately, this also leaks some information, and there were papers on this as well. And in order to cope with that, there are many solutions dealing with distributed differential privacy or batch partitioning. Thank you. Last one, verifiability. So we're dealing with either malicious aggregators or malicious users for the moment. There was a very nice talk this morning on this aspect. So the users or the malicious can just try to poison the model, but the idea of poisoning can be just also a backdoor in order to get some information, so to discover some information about the local data sets as well. To cope with the malicious aggregators, there are many solutions using homomorphic hash functions, so to prove the actual correctness of the sum, or some commitment schemes. Whereas to cope with the malicious users, we mainly compare the result with the threshold value. There are some other solutions that I listened to during these days as well, or also commitment schemes. To conclude, here are our key observations with respect to our analysis in this context. First one is that there are many solutions on masking-based secure aggregation, but each of them are coping with the different, one of the challenges that I mentioned. So can we combine all these and try to come up with the ideal masking-based secure aggregation solution? Then second one, and we're very happy about that, so AHE-based secure aggregation was not that much tackled, was not that much explored. And we succeeded to have a paper on this now, because this was 1 year ago. Some solutions were not secure. We identified that. The observation 4 is very important. So now that we're talking about secure aggregation, we cannot, I think we cannot escape the privacy problems. So we cannot escape the use of differential privacy or multi-round privacy, it's also called in one of the papers. And in terms of verifiability, there are some solutions, as I said, that cope with this problem, but usually they either don't scale with respect to the number of users in the context of malicious users, or with respect to the size of the vectors. That's all. Thank you very much, and I'm happy to answer the questions.
Thank you. So we have maybe like 15 seconds. So unfortunately, no questions at Zulip, but please paste your questions on Zulip and Melek can answer later. Then sure. From me, a very quick question. Since this investigation was performed already like more than a year ago, is there any key insight that you have about the advances in the last year that you would like to emphasize?
So I just discovered, I didn't mention it, I just discovered this Flamingo paper, which is again a masking-based solution, but they tackle the problem of communication overhead with respect. And well, we're working on and I really liked the paper. I repeat always because I really liked it. We're working on the case where both the aggregator and the user can be malicious. So that's a nice topic that we would like to finalize.
Okay, thank you. Good luck with that. Sorry. Let's thank Melek again.